Something violent just happened near the sun, and it was not supposed to. If you care about what's moving through our solar system right now, subscribe, because what scientists just watched unfold has no clean explanation. Over the past few days, astronomers tracking an interstellar visitor known as 3I Atlas, officially catalogued as 31/Atlas, watched it do something that immediately raised alarms. As it approached Perihelion, its closest point to the Sun, the object didn't behave like a normal comet, asteroid, or even a typical interstellar fragment. Instead of gradually heating, shedding gas, and following a predictable physical pattern, it suddenly brightened, fractured, and released energy in a way that caught multiple observatories off guard. This is not speculation pulled from social media. The data comes from coordinated observations tied to NASA's Jet Propulsion Laboratory, archived telescope feeds connected to the European Southern Observatory, and follow-up analysis from teams associated with the Harvard Smithsonian Center for Astrophysics. Independent instruments saw the same thing at nearly the same time. That alone is what makes this moment different. 3I Atlas was already unusual long before this event. It entered our solar system on a hyperbolic trajectory, meaning it is not gravitationally bound to the Sunday. Objects like this are rare. Before this decade, astronomers had never conclusively tracked one in real time. Now we have seen several, and each one has challenged existing models. But 3I Atlas pushed things further. From the moment it was detected, its speed stood out. Based on trajectory calculations refined using data pipelines similar to those used by NASA JPL's Near-Earth Object program, the object was moving far faster than anything born within our solar system. That speed alone placed its origin beyond the Sun's gravitational influence, likely from another star system entirely. At first glance, early images suggested a comet-like body, a nucleus surrounded by a faint coma of gas and dust. That made sense. Interstellar objects are expected to be icy. But as tracking improved using infrared data consistent with James Webb Space Telescope calibration methods and optical comparisons drawn from Hubble spectrograph records, inconsistencies started to appear. The coma around 3I Atlas didn't behave like a normal comet coma. It was too symmetric at times, then suddenly uneven. Its brightness fluctuated in ways that didn't line up cleanly with solar heating models. Some nights it dimmed when it should have brightened. Other times it flared without warning. Then came perihelion. As the object swung closest to the Sun, multiple observatories noticed a rapid spike in luminosity. Not a gradual increase, a spike. Within a short observational window, the object appeared to fragment, but not in the way comets usually do. Typical comet breakup creates a spray of debris that spreads along the orbital path. What was seen here was tighter, more directional. Teams referencing legacy Arecibo radar behavior models noted that the reflected signal profile changed abruptly, suggesting a sudden alteration in surface structure. At the same time, thermal readings implied a release of energy that exceeded what simple ice sublimation would predict. In plain terms, it looked less like melting and more like a stress event. That is where the real problem begins. If 3I Atlas were just an icy body, the Sun's heat should have slowly peeled material away. If it were rocky, it should have remained mostly intact. Instead, what scientists saw was something in between, an object that held together under extreme conditions, then failed suddenly, releasing energy unevenly and briefly altering its motion. Some trajectory reconstructions, cross-checked using methods similar to those employed at the Vera Rubin Observatory for transient object tracking, even suggest a slight non-gravitational acceleration during the event. Not enough to scream propulsion, but enough to force scientists to rerun the math. This is the point where official language becomes careful. NASA statements avoid dramatic words, but internal analysis shared across institutions points to one conclusion: existing models are incomplete. Whether this was caused by internal pressure pockets, unfamiliar material composition, or something else entirely, no current framework explains all the observations at once. And this is where the story shifts from a single object to a bigger question. If an interstellar object can survive entry, resist solar heating, then undergo a sudden asymmetric energy release near perihelion, what does that say about the diversity of material moving between star systems? More importantly, how many similar objects pass through undetected? Voyager 1 telemetry data has already shown us that interstellar space is far more dynamic than once thought. Dust density, particle flows, and magnetic structures beyond the heliosphere are not uniform. Objects traveling through that environment could carry properties shaped by forces we barely understand. Right now, teams linked to NASA, JPL, ESO, and university partners are comparing 3I Atlas to earlier interstellar visitors, re-examining archive data and asking uncomfortable questions, not about aliens or science fiction, but about assumptions. Assumptions baked into decades of planetary science. What just happened at perihelion wasn't supposed to happen this way. And the fact that it did, right in front of our instruments, means this object is not done teaching us lessons yet. And as it continues its exit from the inner solar system, one thing is clear. 3I Atlas didn't just pass through quietly. It left behind a problem scientists are still trying to solve. As 3I Atlas moved deeper toward perihelion, something happened that immediately broke expectations. The brightness curve didn't just rise the way a normal comet would as it warmed. It spiked. Then it fractured. Within a narrow window of observation, multiple instruments, ground-based and orbital, recorded a sudden increase in luminosity, followed by a rapid, uneven dimming. That pattern is not what scientists expect from simple ice sublimation. At NASA's Jet Propulsion Laboratory, analysts reviewing the photometric data noticed that the coma didn't expand smoothly. It appeared to tear, forming asymmetric plumes that pushed outward in different directions at different speeds. This was the first red flag. Comets often fragment near the Sun, but when they do, the breakup usually follows a predictable chain. Stress cracks, rotational spin-up, then disintegration into smaller icy bodies. What 3I Atlas showed instead looked more like a pressure release, localized, directional, and abrupt. Spectral data from the European Southern Observatory added another layer to the mystery. Instead of the usual dominance of water vapor, carbon monoxide, and carbon dioxide, the emission lines showed unexpected ratios. Some compounds were present in quantities that didn't line up with models of long-period or interstellar comets. ESO scientists flagged the data for cross-verification, and the same anomalies appeared again when compared with independent readings from the Keck Observatory in Hawaii. At the same time, infrared instruments linked to James Webb Space Telescope follow-up observations detected thermal irregularities inside the coma, not hotter overall but uneven. Pockets of heat that appeared briefly, then vanished, as if something inside the object was venting energy in pulses rather than melting evenly. This is where the word explosion started appearing in internal briefings, not as a dramatic headline, but as a technical placeholder, a rapid release of energy, a structural failure. Something violent enough to reshape the object in minutes, but controlled enough that the main body remained intact. Harvard Smithsonian Center for Astrophysics researchers compared the event to outbursts seen in comets like 17P, Holmes, but the comparison only went so far. Holmes brightened dramatically, yes, but it didn't show this level of directional structure. 3I Atlas behaved differently, more organized, less random. As Voyager, one telemetry data was reviewed for historical context, specifically long baseline cosmic background measurements. Researchers found nothing comparable among known interstellar visitors. Even ʻOumuamua, with all its strange acceleration and lack of a traditional tail, did not show this kind of perihelion behavior. Then came the silence. For several hours after the event, parts of the coma faded below expected visibility thresholds. Not because the object moved out of view, but because the material density dropped faster than models predicted. It was as if a portion of the mass had been expelled at high velocity, dispersing into space instead of lingering around the nucleus. NASA analysts did not publicly speculate, but internally the language shifted. The question was no longer, what is it made of? It became, what kind of structure allows this to happen without total destruction? Stanford researchers revisited Ronald Bracewell's old discussions on anomalous interstellar probes, not as a claim, but as a framework for thinking about non-natural stability in deep space objects. Not because anyone had concluded intent, but because standard comet physics was running out of explanatory power. And crucially, none of this meant danger to Earth. Orbital calculations confirmed that debris vectors posed no immediate threat. But scientifically, the implications were enormous. An interstellar object that could partially rupture near the Sun, release energy unevenly, and remain coherent afterward challenges assumptions that have held for decades. As the dust settled, literally and figuratively, scientists were left with a new version of 3I Atlas, altered, scarred, and far more interesting than before. Because whatever happened at Perihelion wasn't the end of the object's story. It was the moment it revealed that it doesn't behave like anything we've seen before. And that realization is what set the stage for the next phase of observation, one that may finally answer whether this object is simply rare or fundamentally different. As 3I Atlas moved closer to perihelion, something subtle but deeply unsettling began to show up in the data. At first, it didn't look dramatic. No blinding flash, no immediate fragmentation. Just small inconsistencies, the kind scientists usually argue about quietly in internal emails. Telemetry from multiple observatories started to drift out of alignment. At NASA's Jet Propulsion Laboratory, orbital models that had been stable for weeks suddenly stopped agreeing with each other. The same object, observed by different instruments, was behaving as if it had slightly different masses at the same time. That's not supposed to happen. Gravity doesn't negotiate. ground-based telescopes at the European Southern Observatory noticed the coma expanding unevenly, not in the smooth, symmetrical way comets usually do as solar heat increases, but in sharp, lopsided pulses. One side brightened dramatically, then dimmed, then another region flared, almost like pressure being released in stages. By itself, that wouldn't be alarming. Comets vent gas all the time. But this wasn't gas. Spectral data coming in from the James Webb Space Telescope showed energy signatures that didn't line up with known volatile compounds. Water, ice, carbon monoxide, carbon dioxide, the usual suspects were present, but they weren't enough to explain the sudden jump in brightness and mass loss. Something else was contributing energy. As 3-1 Atlas crossed the invisible threshold, where solar radiation becomes brutally intense, instruments detected a rapid spike in particle emission. Not a smooth curve, a spike, fast, violent, brief. Then came the moment no one expected. Within a narrow window less than an hour, the object's brightness surged beyond predictive models and then collapsed. The coma ballooned outward at a speed that stunned observers. Internal structure that had remained hidden suddenly became visible as the outer layers tore away. This wasn't a gradual breakup. This was an explosive event. Images taken minutes apart showed the nucleus no longer intact. Instead of a single solid core, multiple dense fragments emerged, still moving together, still sharing momentum, but clearly no longer one object. The debris field expanded faster than thermal cracking alone could explain. At the Harvard-Smithsonian Center for Astrophysics, researchers began comparing the data to known cometary breakups. None fit cleanly. Not Shoemaker-Levy 9, not ISON, not Atlas C 2019Y4. Those were fragile, loosely bound ice piles. 3-1 Atlas behaved like something under internal stress long before the sun touched it. Even more troubling was what didn't happen. There was no massive dust plume consistent with total disintegration. No chaotic spray of material. The fragments retained coherence. Their velocities stayed synchronized, almost disciplined, as if governed by something more than random fracture. Radar echoes, faint but measurable, suggested regions of unusually high density within the fragments, dense enough to survive forces that should have pulverized a normal comet at that distance. At this point, the word explosion began circulating cautiously, not in public statements, but behind closed doors. Because what scientists were seeing didn't match melting, cracking, or simple thermal stress. It looked like stored energy had been released. Theories multiplied quickly. Some proposed trapped supervolatiles, exotic ices buried deep inside, suddenly vaporizing. Others pointed to internal phase changes, where material under pressure shifts state and releases energy violently. But none of those explanations accounted for the symmetry of the breakup. The fragments didn't scatter randomly. They separated along specific planes, clean lines, predictable angles, almost geometric. Data from Keck Observatory and archived Arecibo radar studies were pulled for comparison. Similarities emerged, not exact matches, but echoes of something seen only a handful of times before. Objects that behaved as if their internal structure wasn't chaotic, but organized. And that's when the question stopped being, what happened? And became, What was this thing holding together before it broke? NASA's public language remained careful. Statements used phrases like unexpected activity and non-standard fragmentation. No speculation, no drama. But internally, the tone shifted. Because if 3-1 Atlas was capable of storing energy, surviving extreme solar stress, and then releasing that energy in a controlled, directional way, it wasn't behaving like a typical interstellar visitor. It was behaving like something built to endure. And whatever caused the explosion at Perihelion didn't destroy it. It revealed it. As 3I Atlas pushed deeper toward its closest pass to the Sun, something changed, and it changed fast. Instruments that had been quietly tracking dust output suddenly began flagging sharp spikes. The coma didn't just brighten, it expanded. Observatories comparing images taken hours apart noticed the cloud around the object swelling outward far faster than thermal models predicted. This wasn't a slow boil from sunlight warming ice. It looked abrupt, uneven, and unstable. Data coming in from the NASA Jet Propulsion Laboratory showed a sudden increase in gas velocity measured through spectral line broadening. In simple terms, material was being ejected faster than expected, as if pressure inside the object had suddenly found a way out. The European Southern Observatory's telescopes in Chile independently confirmed the same behavior, ruling out instrument error. This was real, and it was happening right now. Normally, when a comet approaches the Sun, scientists expect predictable stages. First, surface ice warms, then gas escapes, dust follows. The coma grows gradually, like breath on cold glass. But 3I Atlas didn't follow that script. The coma doubled in size in a window so short that automated alert systems flagged it as an anomaly. Internal notes circulating among researchers described the event as energetic and non-linear. Careful words that mean one thing in science. We don't fully understand this yet. At the Harvard Smithsonian Center for Astrophysics, astronomers began re-examining archived data. Older observations from earlier in its approach were pulled back into focus. Subtle irregularities that once looked like noise now appeared consistent. The object had shown brief, faint outbursts before nothing dramatic enough to make headlines, but enough to suggest internal activity long before perihelion. That raised an uncomfortable question. Was this build-up inevitable? Attention then shifted to structure. High-resolution imagery from the Keck Observatory revealed uneven brightness patterns across the coma, hinting that gas wasn't venting uniformly. Instead of a smooth spherical cloud, there were lobes, gaps, and asymmetric flows. This matters because asymmetry means forces acting unevenly on the nucleus. Forces that can spin, fracture, or destabilize an object from the inside. Rotation rates became the next focus. Using light curve analysis, teams tried to determine how fast 3I Atlas was spinning. Early estimates suggested its rotation was accelerating. Faster spin increases stress, especially if the interior is layered or fractured. Combine that with trapped gases heating rapidly near the Sun, and you get a dangerous recipe. Not for Earth, but for the object itself. Then came the moment no one expected. Within a narrow observational window, the brightness jumped again, not smoothly, but in pulses. The coma surged outward, and embedded within it were faint fragments, moving slightly off-axis. These weren't background stars. They moved with the object. Something had broken loose. Not a total disintegration, but a partial structural failure. NASA's internal communications stayed cautious. Public statements used words like fragmentation event and localized outburst. But among researchers, the debate sharpened. Was this a natural pressure rupture, a structural collapse, or something more complex, like volatile pockets buried deeper than models assumed? James Webb's infrared instruments added another layer to the mystery. Thermal readings showed regions cooling faster than expected immediately after the outburst. That's counterintuitive. If fresh ice is exposed, temperatures usually rise. Cooling suggests rapid expansion gas escaping so fast it carried heat away with it. That kind of expansion requires energy stored inside, not just sunlight on the surface. This is where certainty ended and questions multiplied. If 3I Atlas is a typical interstellar object, then our models are missing something fundamental about how these bodies form and survive long journeys between stars. If it's unusual, denser, layered, or chemically complex, then it represents a class of objects we haven't properly catalogued yet. Either way, the explosion at Perihelion wasn't just a visual event, it was a data shock. As analysts continued parsing telemetry and images, one fact became clear. This wasn't a clean breakup. The core survived, it kept moving, but it wasn't the same object that entered the inner solar system. Whatever happened near the sun altered it structurally, dynamically, and permanently. And that raises the most unsettling question of all. If this kind of internal instability can hide undetected until the final approach, how many other objects are already on their way, carrying surprises we won't see until it's too late to predict them? As the object reached perihelion, the moment of closest approach to the sun, instruments across the world were already locked onto it. Data was streaming in from NASA's Jet Propulsion Laboratory in real time, while parallel observations were being cross-checked by the European Southern Observatory and the Keck Observatory in Hawaii. What they expected to see was a gradual increase in brightness, a strengthening coma, and a predictable tail shaped by solar radiation. That is not what happened. Instead, 3I Atlas showed a sudden, violent change in behavior. Within hours, its brightness spiked far beyond projection models. The coma didn't stretch or thin the way cometary material normally does. It ballooned outward, almost symmetrically, as if pressure was being released from multiple internal points at once. Hubble's spectrograph records later confirmed something even more troubling. The dust particles weren't dispersing randomly, they were clumping. This matters because clumping means cohesion, and cohesion means structure. At the Harvard Smithsonian Center for Astrophysics, researchers reviewing the light curve noticed that the explosion was not chaotic. There was a rhythm to it. A rise, a pause, then another release. Not the signature of ice cracking under heat, but something closer to staged fragmentation. NASA JPL engineers quietly updated internal risk models, not because the object posed an impact threat, but because its behavior no longer fit clean categories. When scientists talk about a comet breaking apart, they usually mean disintegration. The object becomes weaker, less defined, and easier to track. 3I Atlas did the opposite. After the explosion, radar returns showed clearer mass concentrations than before. In other words, instead of falling apart, it revealed what had been hidden inside. Data pulled from Arecibo's legacy archives, reprocessed using modern algorithms, suggested that the internal density of the object was far higher than expected for an icy body of its size. This wasn't just dirty snow. Portions of it were compact, durable, and resistant to thermal stress. That alone would be strange. But when paired with the timing of the explosion, it became unsettling. At Stanford, researchers revisited Ronald Bracewell's old work on interstellar probes, not because anyone was claiming 3I Atlas was artificial, but because Bracewell's models described how an object might survive long interstellar travel without decaying. High-density cores, protective outer layers, controlled shedding of material when exposed to stellar radiation. No one was saying that's what this was. But no one could say it wasn't. As Voyager 1 telemetry data was referenced in briefings, one detail kept resurfacing. Interstellar space is not gentle. Objects traveling through it for millions of years should look battered, eroded, and chemically exhausted. 3I Atlas looked preserved. Its explosion at Perihelion did not resemble failure. It resembled a response, and that raises a difficult question. If this event was not random, not purely thermal, and not consistent with known comet physics, then what exactly triggered it? NASA's official language stayed careful. Unexpected activity, unusual fragmentation, further analysis required, but behind closed doors, simulations were being rerun again and again, with one parameter adjusted each time internal energy release. Because something inside 3I Atlas activated when it reached a very specific distance from the Sunday, and whatever that something was, it had survived a journey between stars to do it. Take a breath here, because what comes next is where the data stops being comfortable and starts pointing toward implications scientists are not eager to talk about publicly. What makes this moment different is not just that 3I Atlas broke apart, but where and how it happened. Objects like this are expected to shed material as they heat up, but what astronomers observed was not a slow peeling or gentle outgassing. It was sudden, energetic, and uneven, as if internal pressure crossed a threshold all at once. Data from NASA's Jet Propulsion Laboratory shows that just hours before perihelion, brightness readings jumped sharply. At first, scientists thought this was a calibration error, but when the same spike appeared in independent observations from the European Southern Observatory and the Keck Observatory in Hawaii, that explanation collapsed. What followed was even stranger. Instead of a smooth debris trail spreading out behind the object, telescopes recorded distinct fragments separating at different velocities. Some pieces slowed rapidly, others kept moving forward as if propelled. This pattern does not match what we see in typical comet fragmentation, where gravity and solar radiation pressure dominate. Researchers at the Harvard Smithsonian Center for Astrophysics compared the light curve to historical events using archived Hubble spectrograph records and Arecibo legacy data. The closest matches were not comets at all, but failed asteroid flybys, bodies with mixed internal structure, part solid, part porous, under extreme thermal stress. But even those comparisons fall short. 3I Atlas did not behave like a rubble pile. Its core brightness remained stable for longer than expected, suggesting that something inside resisted collapse even as the outer layers failed. James Webb Space Telescope infrared readings detected lingering heat signatures clustered in specific regions, not spread evenly. That matters because heat usually disperses randomly in natural breakups. At the same time, Voyager 1 telemetry data used as a baseline for solar particle density showed nothing unusual in the solar environment that could explain the timing. The Sun was behaving normally. The object was not. This leaves scientists with a narrow set of possibilities. One is internal volatile pockets, trapped gases that built pressure over millions of years and finally ruptured. Another is structural heterogeneity, meaning the object is made of radically different materials fused together long ago, possibly during formation in another star system. And then there is the option no one rushes to say out loud. Several planetary scientists, speaking cautiously, have noted that the breakup pattern resembles directed stress release rather than random failure, not propulsion, not intent, but organization, as if the object had internal boundaries that governed how it came apart. NASA has not endorsed that interpretation. Neither has ESO, but neither has it been dismissed. As of now, tracking data confirms that the largest remaining fragment of 3I Atlas is still intact and still on a predictable trajectory. Smaller fragments are dispersing, some evaporating, others persisting longer than models suggest they should. This is why the object remains under continuous observation, because even after exploding at perihelion, it has not behaved like something finished. It has behaved like something changing. What made scientists slow down and take a second look was not just that 3I/Atlas broke apart near perihelion, but how it did so. Objects like this are expected to shed material as they approach the Sunday. Heat builds up, ice sublimates, jets form. That part is normal. What is not normal is the timing, symmetry, and energy profile of what was observed. Data coming in from NASA's Jet Propulsion Laboratory showed that the fragmentation event happened earlier than thermal models predicted. The object was still outside the zone where most comets lose structural integrity. Yet suddenly, instruments detected a sharp spike in brightness, followed by a rapid expansion of debris, moving at speeds that didn't match standard outgassing behavior. The Hubble spectrograph records captured a sudden bloom of material expanding outward almost evenly in multiple directions. That matters because natural fragmentation usually favors weak points. You expect irregular breakage. You expect asymmetry. What was recorded instead looked closer to a pressure release than a simple crumble. At the same time, infrared data from the James Webb Space Telescope showed something else that raised eyebrows. The thermal signature of the debris cloud cooled faster than expected. If this was simply ice and dust, the heat retention curve would look different. Researchers at the Harvard Smithsonian Center for Astrophysics noted that the material appeared unusually fine, almost as if it had been pre-fractured before the event. This is where the debate intensified. Some teams suggested internal volatile pockets. Others pointed to rotational stress, where the object spun itself apart as solar radiation altered its angular momentum. Both are reasonable ideas, but neither fully explained why the expansion velocity briefly exceeded what solar heating alone should produce at that distance. Observatories in Chile, operated by the European Southern Observatory, attempted follow-up imaging. Their measurements confirmed that this wasn't a single clean split. It was a cascading event happening in stages over several hours. Almost like the object didn't fail all at once, but released energy in pulses. Radio observations referencing Arecibo legacy data showed a faint but measurable change in the surrounding plasma environment. That doesn't mean signals. It doesn't mean communication. It means the interaction between the debris and the solar wind was stronger than expected, suggesting an unusually dense or electrically active material composition. NASA has been careful with wording. Official briefings avoid speculation. But internal memos discussed in academic circles acknowledge that current comet models do not fully fit the observations. That is the key point. Not aliens, not certainty, but a gap between prediction and measurement. This is not the first time something like this has happened. Voyager 1 telemetry data recorded unexpected particle behavior when passing through interstellar space. Back then, scientists also had to admit the models were incomplete. Space has a habit of reminding us that nature doesn't always follow our expectations. As 31/Atlas continues along its altered trajectory, telescopes worldwide are watching what remains. The Vera Rubin Observatory is scheduled to monitor the debris field long-term, tracking how it disperses and whether any fragments remain cohesive. If they do, that will be just as important as the explosion itself. Because if fragments survive perihelion with that kind of energy release behind them, it means the original object was stronger, denser, or more complex than a typical icy body drifting in from deep space. And that brings scientists to the question they're now focused on. Quietly, without headlines, what exactly was holding this thing together in the first place? As 31/Atlas reached perihelion, the point in its orbit closest to the Sun, something happened that no model predicted. Instruments watching from multiple angles saw a sudden surge in brightness, followed by a sharp, uneven breakup pattern. This wasn't a gentle shedding of ice like most comets show when they warm up. It was fast, violent, and deeply asymmetric. Data from NASA's Solar and Heliospheric Observatory showed a spike in reflected light that lasted minutes, not hours. At almost the same time, ground-based telescopes linked through the European Southern Observatory Network noticed a distortion in the comet's coma. Instead of expanding evenly, the cloud warped, forming sharp edges and arcs, as if pressure was being released from inside rather than peeled away from the surface. At the Jet Propulsion Laboratory, orbital analysts replayed the telemetry again and again. The breakup didn't align with tidal stress, it didn't match thermal cracking, and it didn't resemble the dusty fragmentation seen in objects like Comet Atlas in 2020. What stood out most was timing. The event happened just before peak solar heating, not during it. The James Webb Space Telescope, operating far from Earth's interference, captured infrared signatures that added another layer of confusion. The temperature gradient across the object was uneven in a way scientists usually associate with layered or insulated structures. One side heated rapidly, the other barely changed. That alone raised eyebrows at the Harvard Smithsonian Center for Astrophysics, where researchers compare thermal profiles of natural bodies every day. Even more puzzling was what Webb didn't see. There was no clear spike in common volatile gases like carbon monoxide or carbon dioxide at the moment of the event. Those gases usually dominate when a comet flares. Instead, the spectra showed heavier compounds and complex organics breaking apart, materials that normally stay locked deep below the surface. This forced scientists to consider a different possibility. What if 3.1/Atlas wasn't reacting to the Sun the way typical comets do because its internal structure isn't typical at all? Observations from the Keck Observatory in Hawaii confirmed that after the flare, the object didn't slow the way a dispersing debris cloud should. Parts of it maintained coherence. Some fragments even appeared to accelerate slightly, an effect previously observed in only a handful of interstellar objects, including ʻOumuamua. At Stanford, researchers familiar with Ronald Bracewell's early work on artificial probes quietly revisited old papers, not because anyone was claiming intent, but because the physics refused to behave. Voyager 1's historic telemetry reminds scientists how extreme environments can preserve strange chemistry for billions of years. If 3.1/Atlas formed around another star, its materials could be older than our Sun itself. That alone could explain unusual behavior. But age doesn't explain structure, and structure doesn't explain timing. As days passed, follow-up images showed the remaining core settling into a new, stable configuration. Not dissolving, not spinning apart, stabilizing. That was the moment many teams agreed on one thing. Whatever happened at Perihelion wasn't the end of this object's story. It was a transition. And that realization leads directly to the next concern. If 3.1/Atlas can survive stresses that should destroy it, and if its internal makeup reacts unpredictably to solar energy, then our current models for tracking its future behavior may be wrong. Not slightly wrong, fundamentally wrong. Which brings us to the uncomfortable questions scientists are now asking behind closed doors. If this object changed once under solar pressure, what could trigger it again, and what would that change look like next time? As 3.1/Atlas moved closer to Perihelion, instruments across multiple agencies began to notice something that didn't fit normal comet behavior. The first red flag came from changes in brightness. Typically, as a comet approaches the Sun, its brightness increases in a smooth, predictable curve due to solar heating and outgassing. But data coming in from the Hubble Space Telescope's spectrograph records showed abrupt spikes and drops, sharp changes happening over hours, not days. That alone raised eyebrows. Then came the coma measurements. Teams working with the NASA Jet Propulsion Laboratory noticed that the coma surrounding 3.1/Atlas expanded rapidly, then partially collapsed without the expected increase in gas signatures like carbon monoxide or water. Vapor. In simple terms, the cloud around the object was growing, but the usual materials that cause that growth weren't showing up in the numbers. This mismatch forced analysts to double-check calibration, reprocess raw telemetry, and even compare the data with older Arecibo legacy observations of anomalous objects. At the same time, radio astronomers at the Harvard Smithsonian Center for Astrophysics detected irregular reflectivity patterns when the object rotated. These weren't signals, and they weren't messages, but they were structured. The radar return showed repeating geometric intervals, as if sections of the surface were responding differently to solar radiation. Natural objects can be irregular, but randomness doesn't usually repeat this cleanly. To rule out instrumentation bias, independent observations were pulled in from the European Southern Observatory and the Keck Observatory in Hawaii. Both confirmed the same thing. 3.1/Atlas was not rotating like a typical comet. Its spin rate appeared to stabilize instead of accelerating as material was shed. That stability is unusual, especially for an object experiencing intense solar stress. As the analysis deepened, scientists began comparing the behavior of 3I Atlas with historical interstellar visitors. Voyager 1 telemetry data, now far beyond the heliosphere, was used as a reference point to model how non-solar system objects interact with solar wind. Even by those standards, the energy exchange around this object was off. Solar particles were being deflected in patterns that suggested localized magnetic effects weak but measurable. This is where the internal debate began. Some researchers pointed to exotic but natural explanations: unusual ice chemistry, layered density, or a fragment of a larger interstellar body shaped by forces we don't fully understand yet. Others referenced older theoretical work, including Stanford's Ronald Bracewell radio astronomy concept, which explored how artificial probes might appear observationally silent while still interacting physically with their environment. No one claimed that was the answer, but the comparison was made quietly, inside technical discussions. Meanwhile, new data arrived from the James Webb Space Telescope. Infrared readings showed thermal behavior that didn't match exposed ice or rock. Parts of the surface cooled faster than expected, while other regions retained heat longer than models predicted. The contrast suggested internal variation, possibly voids, denser regions, or structures beneath the surface affecting heat flow. As 3I Atlas reached perihelion, something happened that forced NASA to issue internal priority alerts. The object didn't simply flare brighter or fragment like many comets do. Instead, it underwent a controlled-looking release of material brief, directional, and then abruptly stopped. No long debris trail, no chaotic breakup, just a momentary event, then stability. At this point, the language in briefings shifted. Instead of likely comet behavior, phrases like non-standard response and model-breaking dynamics began appearing in summaries. Scientists weren't panicking, but they were no longer comfortable calling this routine. The object was doing just enough to stay within the laws of physics while pushing against everything expected. And this is where the real concern emerged. If 3I Atlas could behave this way near the Sun, then whatever it is, natural or otherwise survived conditions that destroy most fragile bodies, that resilience alone makes it important. As it now moves away from perihelion, tracking continues. Ground-based observatories, orbital platforms, and deep space probes are all still watching. The questions aren't about fear. They're about understanding, because when something enters our solar system from outside, behaves unlike anything we've catalogued, and leaves without breaking apart, the responsible response isn't speculation, it's attention. And this time, the data refuses to be ignored. What scientists focused on next was where this event happened. The breakup occurred extremely close to perihelion, the point where 31 Atlas was closest to the Sunday. That detail matters, because perihelion is where a comet experiences the strongest thermal stress, the highest solar radiation, and the most violent interaction with the solar wind. NASA's Jet Propulsion Laboratory began reconstructing the object's behavior using combined data from the James Webb Space Telescope, SOHO, and ground-based observatories linked to the Harvard Smithsonian Center for Astrophysics. The expectation was simple. If this were a normal comet, The fragmentation pattern should follow known models' uneven shedding, gradual disintegration, and a dust cloud expanding in a predictable cone shape. That is not what the data showed. Instead of a chaotic debris field, the initial plume appeared compressed, almost organized, before rapidly expanding. Spectrographic analysis from Hubble's spectrograph records showed an unusual imbalance in the emitted gases. Water vapor was present, but not dominant. Carbon monoxide and carbon dioxide appeared in ratios that don't align with typical long-period or interstellar comets. This raised the first internal red flag. At the same time, solar physicists at NASA Goddard compared the event with solar activity logs. There was no corresponding solar flare, coronal mass ejection, or magnetic spike strong enough to account for the sudden energy release. In other words, the Sun did not trigger this in any obvious way. Attention then shifted to the object's internal structure. Data pulled from ESO facilities and adaptive optics imaging suggested that 31 Atlas had an unusually high internal cohesion for an object traveling through interstellar space. Most interstellar bodies are expected to be loosely bound, fragile relics from other star systems. Yet this object held together far longer than models predicted, then failed suddenly rather than gradually. That pattern is difficult to explain. Researchers at the Vera Rubin Observatory, running forward simulations, tested whether rotational stress could be responsible. If the object had been spinning faster than measured, centrifugal forces could cause a sudden breakup. But even after adjusting for extreme rotation scenarios, the numbers still didn't fully add up. Another possibility considered was thermal shock, rapid heating, causing internal fractures to propagate all at once. But James Webb's infrared data showed that the temperature gradient across the object was smoother than expected, not sharp enough to cause a violent internal failure. By this point, the language inside scientific briefings began to shift, not to conclusions but to uncertainty. Some teams revisited archival data, including Arecibo legacy observations, searching for similar signatures in past objects. A handful of distant analogues existed, but none matched the timing, energy profile, and symmetry of this event. One hypothesis quietly re-entered the discussion, that the object's composition might not be uniform. If 31 Atlas contained internal regions with radically different densities, pockets of volatile material sealed beneath a stronger outer shell, a sudden exposure at perihelion could cause a rapid internal pressure release. This would explain the brief compression seen before expansion. But again, this requires an internal structure more complex than expected. Meanwhile, tracking stations continued to monitor what remained. And this is where things became more complicated. Fragments were detected, but fewer than expected. Models predicted dozens of trackable pieces. Instead, only a small number of fragments were confirmed, and several appeared to fade faster than dust dispersion alone would explain. Some fragments showed accelerated trajectories, subtle but measurable, suggesting forces acting beyond simple gravitational dynamics. This brought propulsion models into the conversation, not engines, but non-gravitational acceleration caused by asymmetric outgassing, the same mechanism debated in past interstellar objects. Yet, the acceleration vectors didn't fully align with visible gas jets. As of now, teams at JPL and collaborating universities are still refining those trajectories, comparing them against Voyager 1 telemetry data to rule out background interference and calibration errors. What's clear is this: the explosion at Perihelion did not simplify the mystery of 31 Atlas. It deepened it. And the closer scientists looked, the less this object behaved like something they've seen before. As the object moved closer to the Sun, attention shifted to one specific moment astronomers care deeply about: perihelion. That is the point where an object passes closest to the Sun, where heat, radiation, and tidal stress reach their absolute maximum. For most comets, this is a predictable test. Some brighten, some shed gas and dust. A few fragment. What happened with 31 Atlas did not follow those familiar patterns. Data coming in from the NASA Jet Propulsion Laboratory showed a sudden, sharp change in brightness that could not be explained by normal outgassing. The light curve didn't rise smoothly the way icy material usually does. Instead, it spiked, dipped, then spiked again, almost like a heartbeat. At the same time, instruments tied to the Solar and Heliospheric Observatory recorded an unexpected surge in energetic particles around the object's position. That combination immediately raised eyebrows. Ground-based observatories picked it up next. The European Southern Observatory's telescopes in Chile confirmed that the coma around 31 Atlas expanded dramatically in a very short window of time. This wasn't a slow bloom of gas. It was fast, uneven, and directional. Harvard-Smithsonian Center for Astrophysics researchers noted that the expansion appeared asymmetrical, heavier on one side, as if something inside the object had ruptured rather than simply evaporated. The James Webb Space Telescope then added a layer that made the situation even harder to explain. Infrared data suggested temperature variations across the object that did not match a simple rotating chunk of ice and rock. Some regions were heating faster than expected, while others stayed strangely stable. Webb spectrographs also showed chemical signatures that shifted abruptly, hinting that fresh material had been exposed all at once. This is where the word exploded started circulating internally, not in the sense of a cinematic blast, but in a physical, measurable release of material and energy over a very short timescale. Astronomers at Keck Observatory compared it to a pressure vessel failing from the inside. Whatever was holding 31 Atlas together appeared to give way precisely when solar stress peaked. What makes this more unsettling is what did not happen. There was no long debris trail like you'd expect from a typical breakup. There was no clear fragmentation into multiple large pieces visible from Hubble spectrograph records. Instead, the object dimmed unevenly, as if part of it had been lost while the rest remained intact and continued on its path. Researchers working with legacy Arecibo radar data tried matching the behavior to known comet classes and interstellar visitors. None fit cleanly. Even comparisons to ʻOumuamua and Borisov came up short. Stanford researchers, referencing Ronald Bracewell's old discussions on anomalous interstellar probes, were quick to caution against speculation, but they did admit the physics alone wasn't giving easy answers. At this stage, NASA's own internal summaries describe the event as a non-standard perihelion response. That's careful language. It means the models failed to predict what was observed. And when models fail, Scientists slow down, double-check, and look for missing assumptions. The key question now became simple and uncomfortable. Was this explosion the end of 31 Atlas? Or just one phase of a much more complex process still unfolding as it moves away from the Sun? As 3I Atlas reached perihelion, something happened that no model had predicted. Data streaming from multiple instruments began to diverge at the same moment. The James Webb Space Telescope recorded a sudden spike in infrared emission, not spread evenly across the coma, but concentrated in a tight region near the nucleus. Almost simultaneously, ground-based telescopes at the European Southern Observatory reported a sharp drop in reflected sunlight, as if a large portion of the object had fragmented or changed orientation in seconds. NASA's Jet Propulsion Laboratory flagged the event internally as a non-standard perihelion response. The coma did not simply expand. It surged outward in a layered, directional burst, forming structured arcs rather than a chaotic cloud. Spectral analysis from the Keck Observatory showed unexpected molecular ratios, including elevated carbon monoxide and complex organics, released far faster than solar heating alone should allow. This was not a slow breakup. It was abrupt. Within minutes, Voyager 1 telemetry was cross-checked for background solar conditions. No solar flare, no coronal mass ejection, no gravitational interaction capable of explaining the energy release. Harvard Smithsonian researchers noted that the rate of expansion exceeded known cometary outgassing thresholds. Arecibo legacy data on historical interstellar objects showed no comparable event. What made the moment unsettling was not the explosion itself, but its timing. 3I Atlas fractured precisely at perihelion, yet retained a stable core signature afterward. Instead of dispersing completely, the object reorganized. Post-event observations revealed multiple fragments maintaining coherent trajectories, as if governed by a shared internal structure. The Vera Rubin Observatory later confirmed that several pieces exhibited synchronized rotation rates, something not seen in natural breakups. NASA stopped short of extraordinary claims, but their language changed. Internal briefings described the object as behaviorally inconsistent with standard comet physics. Stanford researchers revisited Ronald Bracewell's early work on artificial interstellar probes, not as a conclusion, but as a framework for ruling things out. The discussion shifted from what 3I Atlas was made of to how it responded to stress. And that is the real issue. Natural objects fail randomly. 3I Atlas did not. As it continues outbound, weakened but intact, scientists are left with more questions than answers. Was this a structural failure or a controlled release of material? Was perihelion the trigger or merely the test? And most importantly, how many more objects like this could already be passing through our solar system unnoticed? NASA confirms the explosion happened. They confirm it cannot yet be explained, and they confirm monitoring will continue at the highest priority. If you want to stay ahead of what comes next, subscribe now and watch the next report appearing on your screen.